In this lecture, we will be covering the autoregressive conditional heteroscedasticity 1 process, or the ARCH1 process. So to review, we have this idea, this concept of conditional variance. So if we have a square integrable random variable x, real valued on our probability space omega fp, and script g is a sub-sigma algebra of script f, the conditional variance of x given g is defined as the random variable depicted here in equation 1. So note that this conditional variance of x given g is nothing more than the definition of variance or unconditional variance with the addition that the expectations are conditional expectations, conditioning on the information in G. Further, we extend that to the conditional variance of x given the random variable y via equation 2, where this conditional expectation given a random variable is shorthand for the conditional expectation of that random variable given the sigma algebra or information set generated by the random variable y, which is the smallest sigma algebra containing all the information resolved by the variable y. When we want to model non-constant conditional variance, we're dealing with a term called conditional heteroscedasticity. So heteroscedasticity simply means a process or a time series has non-constant variance. If it has conditional heteroscedasticity, it means that the conditional variance of the process or time series is not constant. The standard models that we work with, where we lack these properties, which we would call homoscedasticity, and we're using hetero for different, homo for same, but the homoscedasticity processes we often see look like this, where you have essentially a regression of the response variable yt onto predictor variables x1t up through xpt plus a white noise term. In such a model, we have a constant mean, constant conditional mean, and a constant conditional variance. And we have to make some modifications to allow for non-constant conditional variance or conditional heteroscedasticity. And the key change will come in this white noise term. So this term here is the key. And remember the definition of a white noise, at least a weak white noise, is these epsilon t's would be uncorrelated in time, mean zero, constant variance. So this is the term that we will adjust. And we do it in the following way. So first, we change the epsilon t's to be a white noise with a variance of 1. And we typically call these innovations. Because of the properties of white noise, as we just mentioned, they're uncorrelated in time, which means the expectation of epsilon t given the prior white noise terms is 0. The same thing as just the unconditional expectation. And the variance of epsilon t given the previous values of the epsilons is 1. So this type of white noise process has conditional homoscedasticity or is homoscedastic. The modification that we will make in our new approach is here in this new noise term. And so we want to think of this as being a scaled white noise. And the idea is that this epsilon, having mean 0 and variance 1, this epsilon t, having mean 0, will cause this entire new noise term to be mean 0. But because it has variance 1, the variance will be determined by this sigma function. And the key thing to recognize here is that this sigma has dependence on the predictors. But that is the key. The key is really to think of this as a new noise term. And the first type of process we will look at for such a noise term is the Arch-1 process. So the definition of the Arch-1, or the autoregressive conditional heteroscedasticity 1 process, is as follows. So AT equals epsilon t, which is one of our white noise 0-1 processes, times root alpha naught plus alpha 1 AT minus 1 squared. The restrictions on the parameters, alpha naught and alpha 1 must be non-negative, and alpha 1 must be less than 1. The result of these assumptions, the results of those are that the variance of AT will be finite and AT will be stationary. We can think of this alpha 1 term as a memory term. So as in something like an AR1 process, we have an autoregressive property here in that AT has some memory from its past. And it's more natural to think of this equation if we square both sides. So if we square both sides, that becomes AT squared is epsilon t squared times this expression in the parentheses. And we're rewriting that equation here as equation 8. And note the similarity between this arch process when we write it for AT squared. Note its similarity to our AR1 or autoregressive 1 process YT. So remember that the AR1 process, this is setting mu equal to 0. So YT remembers a piece of what it was yesterday plus a noise term. The Arch-1 process here is saying the square of the Arch-1 remembers a piece of yesterday's squared term plus a constant, but multiplied by a noise term squared. So this looks a lot like the AR1 with multiplicative instead of additive noise. So if we changed this this addition to multiplication and threw a constant in here added to phi YT1, we would obtain something that looks like 8. And so this is really the key to understanding the Arch-1 process. And it really is that we're building in some dependence on the square. We're building in, you'll see here, that because of the similarity between equations 8 and 7, the autocorrelation function for AT square matches that of the AR1. And recall that the autocorrelation function of the AR1 is rho raised to the absolute value of h for integer values of h. Remember, so what this looks like So this is our autocorrelation function. In this case, for the process, we'll say a squared. So this builds in, this definition builds in this autocorrelation structure to the square of the Arch-1 process. And really the key thing to recognize here is that this epsilon t square, right? That's our standard noise term. So mean 0, variance 1. This being squared here means that this dependent structure will affect the conditional variance. And so this is what will give us conditional heteroscedasticity, or a non-constant conditional variance. That looks ahead a bit. Let's actually just step into the properties of this arch 1. So first, let's compute its expectation. So we have the definition of the arch 1 here. To compute its expectation, we're taking this expectation, and we note that epsilon t is independent of a t minus 1 square. So note, if you wrote equation 10 for a t minus 1, you would say a t minus 1 is epsilon t minus 1 root alpha naught plus alpha 1 a t minus 2 square. And so we see everything here is happening at a time prior to time t. We have an epsilon t minus 1. We know the epsilon t and the epsilon t minus 1 are uncorrelated, and we also know in this a t minus 2 squared term, we have an epsilon t minus 2, which is also uncorrelated with epsilon t. And that allows us to say the expectation of the product is the product of the expectation. And we know from the distribution of the innovations, the expectation of epsilon t is 0. So this is a mean 0 process. If we want to compute its conditional expectation, and so remember, we're doing this because we want to look at not only its mean and its variance, but also its conditional mean and its conditional variance. So to compute the conditional expectation of AT, conditioning on memory on the past, values of the A's, so AT minus 1, AT minus 2, so forth, we have conditional expectation of, we replace AT with the right-hand side from its definition. And again, we're conditioning on the past here. But we note that this expression under the square root sign is known, right? It's known from our information set on which we are conditioning, which means, using the property of conditional expectation, we can take it out of the conditional expectation. So this becomes the square root of alpha naught plus alpha 1 a t minus 1 squared times the conditional expectation of epsilon t given a t minus 1, a t minus 2, and so on. Often when we cite rules for manipulating conditional expectation, we say this is taking out what is known. And recall that we can think of that as, because we are given AT minus 1, AT minus 2, so on. Given AT minus 1 means everything in this expression we know. Alpha naught, alpha 1 are constants, and we can get AT minus 1 squared because we know AT minus 1, which means we don't need to guess at it. So it comes out of this conditional expectation. Well, we know that epsilon t is uncorrelated with the previous epsilon t, t minus 1, t minus 2, which are embedded in these terms that we know. But because they're uncorrelated, this expectation can drop the conditioning. And so we're left with expectation of epsilon t. And again, that's because epsilon t is uncorrelated with those prior terms. And we know that this expectation is 0 because the innovations have mean 0. And so we see that this conditional expectation of AT given the prior values of the A's is in fact 0. One thing we can think of here is recall that we are trying to come up with a candidate for a new noise term. So let's go back to what was inspiring us. We had said in order to introduce this idea of conditional heteroscedasticity, we want a new noise term. What are good properties for a noise term? Well, 1 means 0. So we have that. Our new noise term, our candidate for a noise term, our arch1 process, AT, has mean 0. It also has conditional mean 0. So that means if you're trying to guess at AT and you know the previous values of the arch1, that doesn't help you. Your best guess at AT if you don't know anything is 0. Your best guess at AT if you know the previous values is still 0. That is a good property for this expanded noise term, this new noise term, where we're trying to build in this conditional heteroscedasticity. So these two properties we just developed really show us that this is a reasonable candidate for a new noise term. Now we move to the second moment, which we'll do in the opposite order. We'll do the conditional variance first. And so the conditional variance of AT, given its past values, the notation we will use is sigma sub t squared. So sigma squared will be the variance of AT. And you can think of that, we will say that's the unconditional variance. We put a subscript of t to denote the conditional variance, specifically saying the variance of AT conditioning on the previous values of the A's. And so let's compute this. So the definition of conditional variance, if we go back to our first slide when we reminded ourselves of the definition, it's nothing more than the variance of AT with the expectations changed to conditional expectations. So in here, we have AT minus its conditional expectation, all squared. And we're taking the expectation of that, but it's its conditional expectation. Well, note, in the previous step, we calculated that this conditional expectation was 0. And so this simplifies to just the expectation of AT minus 0 squared, conditioning on the previous values of the A's. And we can take AT squared from our definition of the arch1 and plug that in here. So this, again, comes from our definition of the arch1. And now we use properties of conditional expectation, again, noting that this is known. As in the prior calculation, alpha naught, alpha 1 are constants. And at minus 1 squared we know because we're given at minus 1. And the taking out what is known property allows us to factor that out of the conditional expectation. And so that results in alpha naught plus alpha 1 at minus 1 squared times the expectation of epsilon t squared given the prior values of the a's. And the same kind of argument that we made before, the epsilon t square is uncorrelated with everything in here. There's no information with what's in here. That helps us in terms of an expectation. So we can drop the conditioning and we get alpha naught plus alpha 1 a t minus 1 squared times the expectation of epsilon t squared, which is by definition 1. And so we see this simplifies to the expression alpha naught plus alpha 1 at minus 1 squared. And this is the key result. And we'll talk about this more in a minute. But this is so important because the conditional variance, and you can think of that as if you get to watch the previous values of the arch process, what's your guess at the variance for time t? Your guess at the variance for time t is this expression here, and the square of yesterday's value for the arch process is in there. So this has memory. Your conditional variance, your guess at the variance today, if you get to remember the past, has this term that is from the previous time step showing up. To compute the variance of the arch 1, we take our equation for the conditional variance, and we take advantage of the fact that, as we mentioned earlier, at is stationary. And we take the expectation of both sides. And in doing so, we can note that this expectation here, we can use the rule of iterated expectations and say this is the expectation of the conditional expectation of at minus 1 squared given at minus 2, at minus 3, so on and so forth. And this is our definition of sigma t minus 1 squared. Going back here to the definition of the conditional variance. So, in particular, we should mention this is sigma t minus 1 squared because that conditional expectation of at minus 1 given at minus 2, so on and so forth, is 0, which makes this the equation for the conditional variance time t minus 1. So this equation becomes the expectation of sigma t square equals alpha naught plus alpha 1 times the expectation of sigma t minus 1 squared. And now we use the stationarity to note that this expectation of sigma squared at time t minus 1 is the same thing as the expectation of sigma squared at time t. And we now can solve for this expectation. So when we do that, we bring this term to the left-hand side of the equation, and we get the expectation of sigma t squared times the quantity 1 minus alpha 1 is alpha naught, or the expectation of sigma t squared is alpha naught over 1 minus alpha 1, and the expectation of the conditional variance is the variance. So we have now an expression explicitly for the variance of our process. And so when we summarize here, we have everything for the first two unconditional and conditional moments. And note, by the way, we require alpha naught and alpha 1 greater than or equal to 0. And we require alpha 1 also less than 1. And you can see the alpha 1 less than 1, or really the alpha 1 being between 0 and 1, excluding 1, makes sense when we see this variance. So you can't have an alpha 1 greater than 1 because this would be a negative expression. And you can't have an alpha 1 of 1 because you would have a 0 in the denominator. And so we see these assumptions making sense with this expression. So the key thing to recognize here, one, is that this arch-1 process is heteroscedastic. Homoscedastic. And it's homoscedastic because it has a constant mean and a constant variance. But conditionally, it is heteroscedastic. So it is conditionally heteroscedastic. And specifically there, this is happening because we have the non-constant conditional variance. Not only is it homoscedastic, but note that it's weakly stationary. Remember, the definition of weakly stationary means the process has a fixed mean and a fixed variance, which we see here. So thinking about this, remember the idea was we want a candidate for a new noise term. This AT with these four properties makes it, this is a nice candidate for a noise term. It has mean 0. It has conditional mean 0. So think of it as a noise term. It averages 0, and if we get to look at the previous noise terms, our guess at it is still 0. It's weakly stationary, so it has a constant variance. But the change is in this conditional variance. So it's this modified noise term where, again, the variance of the noise term at time t, your guess at that, if you get to watch the previous terms, is this expression which depends on the previous term. And that is the key property. So the other properties are important in that it is a good candidate for a noise term, but this builds in this memory for the conditional variance. And that's really the key. The conditional variance remembers something about the previous time step. And this causes regimes in the conditional variance. So think of it this way. If your previous noise term, so AT minus 1, is large, then because of this expression, well, what does that mean? That means it was a large deviation from its mean of 0. And the conditional variance at the next time step, at time t, remembers that big value for AT1. And since that results in a large conditional variance, that means AT is likely to have a large deviation from its mean of 0 because of this memory yesterday, from yesterday's arch value. So large values in these arch processes tend to propagate through iterations. You can also make the same argument if AT minus 1 is small. If AT minus 1 is small, AT minus 1 squared is small. So the conditional variance of AT at time t will also be small, so you should expect a small deviation from the mean of 0. So you get regimes of small values for AT. And so you get this gives you this clustering effect. And these trends, this unusual conditional volatility trends, tend to persist. But in the long term, because the ATs are stationary, you will always be reverting to the unconditional volatility or the unconditional variance of sigma squared being alpha naught over 1 minus alpha 1. This becomes particularly useful in financial modeling and in risk management because it's often the case for things like, say, returns on an asset or losses on an asset. We often see that the mean doesn't change as much, doesn't change so much, but the variance does. And using a conditional heteroscedastic model allows us to capture that change in the conditional variance via this mechanism. So this introduces some dependence. If there's memory, if the conditional variance is remembering something about the past, we need to look at the auto-dependence of the Arch1 process. And so the first step in doing so is to look at the autocovariance. So recall the definition of autocovariance at lag h, where we assume h is a natural number. Remember, h can be any integer, but gamma of h will actually, in the solution, will actually have the absolute value of h. So we can assume without loss of generality that h is a natural number. So by definition, the autocovariance for A of h is the covariance between AT and AT plus h, which, using the definition of covariance is this expression here. And we know already from our previous computations that the expectation of the Arch1 process is 0. So this expression is reduced to the expectation of AT times AT plus h. And if we use the definition of AT, we have the expectation of epsilon t times the square root of alpha naught plus alpha 1 AT minus 1 squared. And then for AT plus h, we have epsilon t plus h, square root of alpha naught plus alpha 1 a t plus h minus 1 square. And we note, because h is a natural number, so it's at least 1, this innovation term is at a later time than any other term in the expression. And so that means this epsilon t plus h is uncorrelated with all the other terms, which means we can write the expectation of this product as a product of the expectations. So this becomes the expectation of epsilon t times the square root of alpha naught plus alpha 1 a t minus 1 squared times the square root of alpha naught plus alpha 1 a t plus h minus 1 squared. All of that times the expectation of epsilon t plus h, and because it's one of the innovations, we know its mean 0. And that causes this to be 0. So we have 0 autocorrelation for the Arch1 process for lags of 1 or larger. If we recall that the autocorrelation function is, so rho sub a of h is the autocovariance function normalized by the variance we see that that's a 0 in the numerator, which is 0. So we have no autocorrelation or autocovariance for lags in size bigger than 0. So this is interesting. And this also makes AT a nice candidate for a new noise term because they are uncorrelated. They have 0 autocorrelation for lags bigger than 1. But recall that earlier we talked about the autocorrelation function for AT squared. So the autocorrelation for AT square matched that of the AR1 process. And recall that that looks like this. So this is the autocorrelation function for the square of the Arch1 process. So we have dependence between AT and AT plus H via the autocorrelation of the square of AT of AT and AT plus H. So this non-constant path-dependent conditional variance introduces what we could call autodependence, but it happens in the square of the process, not in the process itself. And so this is an example. You hear about this a lot in probability theory when you first learn the idea of independence, dependence, and the idea of correlation. And so what you have is a classic example where AT and AT plus H as a pair, so for H in size larger than 0, these are uncorrelated but they're dependent. And again, the dependence comes into play because of the conditional heteroscedasticity, because you have this autocorrelation structure in the square of the process. And again, this becomes extremely helpful in many different applications where you want to have a noise term that has some kind of memory capability in it for the second moment. In financial modeling, this is extremely useful, and we will talk about applications of this in future lectures, which I encourage you to watch.